All right, so here I am trying this again. Hopefully this recording will work. I am crossing my fingers. Let's get started. Okay, so we are doing 9.1, which is sequences and series. A lot of what you're learning in this particular section, you're going to need again when you go into calculus. Some of it will come up again next week, so definitely, keep your notes. So 9.1 covers using sequence notation to write terms of sequences, using factorial notation, using summation notation to write sums, finding the sums of series, and using sequences and series to model, and solve real-life problems. I'm not going to cover the real-life problems. That's what the application assignment is for. I am going to show you all the notation and how to do a wide variety of problems. So starting with the sequence. A sequence is an ordered list of numbers with a pattern. Like you've heard of the Fibonacci sequence. It's just you've got a series of numbers and there is a pattern to it. So we have an infinite sequence if it just goes on forever. Otherwise, it's a finite sequence if it does eventually stop. And each number is referred to as a term. Our notation for each term is to use the letter A, and then there's a subscript to number the term. So we always start by counting with 1. So the first term is A1, second term is A2, and so on. So my first example here, we are going to write the first 5 terms of a to the n equals 1 minus negative 1 to the nth power, then graph the sequence. So an is just our notation for any term, the nth term, and so to get the first 5 terms, you plug in numbers 1 through 5 in for n. So it's pretty straightforward to first find the first 5 terms. So a1 is equal to 1 minus negative 1 to the first power, which is 1 minus negative 1, which gives you 2. Oh, I should write not an, a1. Second term is a2, 1 minus negative 1 squared, so that's 1 minus 1, which is 0. A3, 1 minus negative 1 to the third power, which is going to be 1 minus negative 1, which is 2. And you notice that there's going to be a pattern here because you're just basically switching your signs from 1 to negative 1 when you're adding on, or you have that 1 minus, and then it's either going to be 1 or negative 1. So once you do enough that you find a pattern, that means a to the fourth is going to be 0, a 5 or a fifth. Fifth term is going to be 2. So when it says graph the sequence, you could just graph this by hand, but Desmos actually has a way to graph sequences, and I took one of their, they have like a tutorial, and then I just modified it for this particular example. And so I have the link here, so you can click on this. This will open it up. And let me just pull this over so that you guys can see this. So they were doing this for 1 over n. I modified it for what we have. So first you start with putting how many numbers you want in the sequence there. So we're going to have 5. You don't really need that blank there. This is how you write. This should say x here. Apparently it works even if it says n, but that should say x. And so you just want to have, we're just writing a function where you're plugging in each term, and then we're writing n, and then we're making ordered pairs basically here, and we're making ordered pairs, making a list from 1 to capital N. So if you wanted to do this to graph other sequences, the only thing you need to change is how many terms, and then you change this part. Make sure you use x or n. N worked because of this part as already in terms of n, but you really should use x because they're defining it as x here. So they did this for 1 over n. This is what we've got. You can see the pattern is going from 2, 0, 2, 0, 2, and if I increase And yeah, it just keeps repeating the pattern. So that's the graphing the sequence. To show you the 1 over n, you would have to type 1 over x, and then that would graph that particular sequence. You can see that that one decreases because you're getting larger and larger numbers in the denominator, so it's going to keep getting smaller and smaller and smaller, and you can see that it's getting closer and closer to 0. So that's how you can graph a sequence using Desmos. So I just searched Desmos and sequences, I found this, and then modified it for my own use. Okay, so that's example 1. Let's take a look at example 2. Write an expression for the apparent nth term of the sequence. 0, 3, 8, 15, 24. And so now we're trying to write what the formula would be to create that sequence. So I find it's easier to kind of make a table of values where you have n as your input and then your sequence value a n as your output. So I've got 0, 3, 8, 15, 24, and our n always starts at 1, 3, 4, 5. So I have 5 terms here, and I need to try to find the pattern. The first way I always do is to see if there's any pattern with adding or subtracting, because that's the easiest thing. So I'm adding 3, then I'm adding 5, here I'm adding 7, here we're adding 9. So I'm not adding the same amount each time, so that's not really giving me a pattern. I'm adding a different amount each time. So that's, that looks like, okay, that's going to be interesting to try to figure out how to write a pattern that way, when not only is the number changing, but the amount you're adding changes each time. And to kind of get some relationship with your n values, that's going to be a little tricky. The other thing I look at then is to see, well, is there am I multiplying by the same number each time, or is there some pattern there? But looking at these aren't even, there's not even a clear multiplication here, because you can't really go from 3 to 8 and 8 to 15, you'd have fractions, and I don't think that's going to be an easy way to do this. But one thing I do notice is that there's some sort of relationship between the n and n squared, because if you look at my terms, each of these are 1 less than a perfect square, because we've got 4, 9, 16, 25. So if I had n squared, all of these are 1 less. 3 instead of 4, 8 instead of 9, 15 instead of 16, 24 instead of 25. So I could conjecture that my pattern is n squared minus 1. So what would that be? So our n squared for n equals 1 is 1. 1 minus 1 is 0. Well, okay, 4 minus 1 is 3. That works. So I just kind of look, well, wait a minute, all these numbers are related in some way. They seem to be 1 less than a perfect square, and that allows me to get my sequence. Now this is a different sequence. So again, we have 5 numbers here. 1, 2, 3, 4, 5. And then I'm going to just write my terms, 91, 82, 73, 64, and 55. So same process, same thought process. I'm going to start looking to see if there's an adding or subtracting pattern. And so from 91 to 82, we're subtracting 9. 82 to 73, I'm subtracting 9. Subtracting 9. Subtracting 9. So this is easy. Oh, okay, I'm subtracting 9 each time. So this will give me a base for how to start. So I'm starting with 91, and then I'm subtracting 9. But I have to do it for each term, so let's do 91 minus 9n. Well, if n is 1, then that would actually give me 82. That would give me the term for n2, not for n1. But if I do n minus 1, then when n is 1, that's 1 minus 1 is 0. I'm not subtracting 9. When n equals 2, I'm only subtracting 9 once because 2 minus 1 is 1. That gets me my 82. And then you can verify, okay, n equals 3. I subtracted 9 twice. That gets me my 73. And so that will work for my pattern. I can simplify this if I want to write it, and it'll look more like a linear equation because we are having a constant amount of change. So that's 91 minus 9n plus 9, which would give me 100 minus 9n. So that is an alternate way to write this sequence. 100 would be the 0th term if we started counting at 0, because then you're just subtracting 9 each time. Example 4 here is a little tricky because we're just alternating between 1s and 3s. Well, how do you write that? So we've got our n, and a to the n. I'm going to just write this. 1, 2, 3, 4, 5. We have 1, 3, 1, 3, 1. Okay, so, well, I'm adding 2, subtracting 2. Adding 2, subtracting 2. So there seems to be some sort of pattern there. So that's where I would start. So I would look at this and say, okay, well, I'm alternating values of 2, so I can take 2 and multiply it by -1 to some power n. That will give me my alternating sign. But I don't just go positive 2, -2. I also have some number that I start with, some missing term here, in order to get me to the 1 and the 3. So I just kind of have my base there, and then I try to figure out, okay, what could that missing term be? Actually, I'm going to write this up here so that I have some room. So I have sort of a guess, but I'm not quite sure if I'm there yet. So let's just say, okay, well, let's just start by plugging in numbers. So for the first one, I have 2 plus -1, and n is 1, plus some unknown, which I can call x. That is supposed to get me a value of 1 when I'm done. So that would be -1 to the first power is -1, so that's -2 plus x equals 1. So x would have to be 3. So now, okay, let's see if that works for the next term. 2 times -1. Now my n is 2 plus 3. What does that get me? So that gives me -1 squared is 1, so that's 2 plus 3. That's 5. Okay, that did not work. So that kind of gave me the wrong thing. So this is like now I know where I'm supposed to be going with this, but I'm kind of showing you the thinking process here. It's like, okay, that didn't work. That actually got too big, but it worked for the first one. And let's just go one more just to see. -1 to the third plus 3. So that would be -2 plus 3. See, that gets you to the right one. So it's just that the even ones that it's not quite working out with. So it's like the difference, it's like too big, too much in a way. So I'm looking at this and I'm thinking, well, I know I have to alternate signs. So let's instead, I'm going to just erase everything I have here so I can kind of mess around. And let's just stick with the alternating signs. Let's get rid of that 2 in front. And maybe that 2 will be taken care of some other way, because clearly that didn't quite work. So let's start again with n equals 1. So I have -1 to the first power plus some unknown, and I need to get 1 out. So that would be -1 plus x equals 1, which would be x equals 2. Okay, so now let's try x equals 2 for the next term. I have -1 to the nth, which would be 2, plus 2. Does this give me 3? So -1 squared is 1, so that is 1 plus 2, that equals 3. Okay, that works out. Let's try it again. -1, third power plus 2. So that's -1 plus 2. That gives me 1. And this is looking good. This is looking like this is our missing term. So I can erase this box because now I've figured out what it is. We have 2. So our magic expression here is -1 to the nth power plus 2. Now the next thing that we talk about in 9.1 are recursive sequences. So a recursive sequence is created when you're using the previous term to get the next term. In order to start a recursive pattern, you need to first know what the first term is so you know where to start, and then you need to know the pattern. Not every sequence can be written recursively. The ones that can be usually are ones where you're adding the same thing each time, or subtracting the same thing each time, or you're multiplying or dividing by the same thing each time. If you're not doing something like that, then you can't write it recursively. For example, example 4 that we just finished here, this would not be something that you can really write recursively. However, example 3, because we're just subtracting 9 each time, all you're doing is subtracting 9 from the previous term. That is something you can write recursively. And so if you wanted to do that, you would start with your first term, which is a to the 1 equals 91. And then you would write a to k, so k would be your next term, equals a, the k minus 1, that's the previous term, minus 9. And then you have to say that k is greater than or equal to 2, because for the k minus 1, that will give you a 1, so that way you can start with that first term. So that just shows you're just subtracting 9 from the previous term. And so that's a recursive way to write it instead of the way that we wrote it before. Recursion is something that actually comes up a lot with programming. It's a more efficient way to code. So if you are taking programming classes, you may have already seen the concept of recursion before. So here's example 5. Write the first 5 terms of the sequence defined recursively. So we're giving A1, we're told that is 3. So that's the first term. We've got that already. We need the first 5. So A2, so k is equal to 2. Or k is equal, actually, we have k plus 1 here. So 2 is equal to k plus 1, which means that 1 is equal to k. So that means a to the k, so a1 minus 1. So then we take a of 1, which is 3. So we have 2 times 3 minus 1, which is 2 times 2, which gives us 4. I don't particularly like to define my recursion as k plus 1 and a to the k. I like to do k and then k minus 1. I think that's a little more intuitive when you're talking about the previous term. Now, a3, so the previous term would be a to the second, or a sub 2, a2 minus 1. So that's 2 times 4 minus 1, 2 times 3, which is 6. And we have a4, which is 2 times a3 minus 1, which is 2 times 6 minus 1, 2 times 5, which is 10. And then a5, our 5th term, 2 times a4 minus 1, 2 times 10 minus 1, 2 times 9, which is 18. Recursion is really great on the computer, but if I asked you to find the 50th term and it was defined recursively, the only way for you to do that would be to write all the other terms, find all 49 previous terms, and that takes a long time. It's a lot easier if you haven't, if it's defined not recursively, like in example 3, because then all you have to do is plug in whatever your n is, like 50, and you can find it immediately without finding all the previous terms. But for programming, this is really easy because you can write a function that uses its input and just send to the function the new input, and it can keep computing as long as you know when to tell it to stop. Next concept is the factorial. So if n is a positive integer, then n factorial, and I'm going to zoom in here, oops, is defined as n, and then we have the exclamation mark, exclamation point, and then 1 times 2 times 3 times 4, and so on until n. And 0 factorial is always defined as 1. So it's not 0, it's 1. So an example, I usually write these a little differently. So if I did, like, say 5 factorial, I always start 5 times 4 times 3 times 2 times 1. I find it a little easier to go counting down rather counting up. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1. So 5 factorial is equal to 120. So I've got my calculator here, and I'm going to show you how to do it on my this calculator, and I have a graphic calculator too. Hopefully the battery hasn't died on this one. So this is the this is really bad. Try it, it's mirror image. TI-30X2S. So to do factorial, so first let's say I want to do 5 factorial. So I have to hit 5. Okay. And then it's this PR, where's my finger? Oh, this mirror image is crazy. Okay, PRB. That's the button. So I hit PRB, and then I have these 3 options. The first 2 options we'll talk about next week. It's the last one, the exclamation point that we need. So I'm going to just scroll over there, and then I need to hit my enter button. Okay, I've got 5 factorial. I hit enter, 120. So that does the factorial. Now, let's see if I can remember how to do it. This is the TI-89 titanium. I knew how to do it on, oh, the battery is dead. Never mind. I had a feeling that the battery was probably going to die. They're not even rechargeable batteries. Okay. I'm going to pause for a moment, see if I have some batteries, and then come back. Okay, so I do not have batteries for my graphing calculator, so I cannot show you where the factorial is on the graphing calculator. I did check on my phone calculator. It does not have factorial. So you want to make sure you know where that button is on your calculator so that you can use that. You want to make sure you have, otherwise you could do it by hand, but if you have really large numbers, that would not work. So, okay, I'm going to go back to the presentation and continue. Okay, so we've got our factorials here. Let's see how to use these. So here's an example of writing the term of a sequence with a factorial involved. So we want to write the first 5 terms of this sequence. And so that's going to be A1 is 1 over, parenthesis, 1 plus 1 factorial. So that is 1 over 2 factorial, which is just 2 times 1, so we get 1/2. That one's easy enough to do in your head. Second term, 1 over 2 plus 1 factorial, 1 over 3 factorial, which is 1 over 3 times 2 times 1. Now if you notice, that's basically 3 times 2 factorial. So you can just take your previous answer and then multiply it by your next term, and you're going to get 1 over 6. A3, 1 over 3 plus 1 factorial is 1 over 4 factorial, which is 1 over 4 times 3 factorial. So 4 times our 3 factorial, which gave us 6, is 1 over 24. A to the 4th is 1 over 4 plus 1 factorial, which is 1 over 5 factorial, which is 1 over 120, because we saw that on the previous slide. And then I got to squeeze this in. A to the 5th is 1 over 5 plus 1 factorial, 1 over 6 factorial, which is essentially just 6 times 120. 6 times 12 is 72, so that's going to be 1 over 720. So those would be the first 5 terms of this sequence. You can see they're getting smaller and smaller and smaller. Okay, so example 7, simplify the factorial expression. This is something that will come in handy next week, which is when we're going to be talking about combinations or permutations. So I'm going to show you how to do that here because it is part of 9.1, but keep in mind you will use this next week. So 12 factorial, I can just write it out. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You can see that's a lot to write out. Then 4 factorial, 4 times 3 times 2 times 1. And then 8 factorial, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Notice that those are all in common, which means those can be basically canceled out. And one alternate way that I would have written this would be maybe 12 times 11 times, or let's just do this on the next line. 12 times 11 times 10 times 9, and then recognizing that 8 factorial is the next part, so that way basically these 8 factorial parts cancel out. So all of those cancel, and then I'm left with the things that are not highlighted. So I have 12 times 11 times 10 times 9, 4 times 3 times 2 times 1. And then you can start canceling out more things. So for example, 4 times 3 is 12, so that can cancel out with the 12. Now all I have left is 2 in the denominator, which I can divide the 10 by 2 and be left with a 5. So that leaves me 11 times 5 times 9. 11 times 5 times 9, which comes out to 495. And then I only have 1 in the denominator, so that's just divided by 1. So you can simplify your factorial expression by using the same thing that you would do if you were reducing fractions. You cancel out common factors. Moving on, we have summation notation, and this is going to show up again when you get to calculus, so this is important to understand now. So when we have a sequence of numbers, and then we say we add all of those numbers together, we are using summation notation, and what we have now is a series, because now we are adding these things together. So it's also called sigma notation because the symbol is actually the Greek letter sigma. It's actually capital sigma. The lower level, lowercase sigma looks differently. And so here's how it's written. We have our Greek letter sigma. The number in the denominator, or underneath it basically, I equals 1. That just tells you where you start. So you're starting, you're counting at 1. The number on top tells you when you stop. So you would stop at whatever n is. And then what's right next to it is AI, and that's just telling you what your sequence is. And so here it would just be A1 plus A2 plus A3 plus A4, and so on. So n is called the upper limit, 1 is the lower limit, and then that I is called the index of summation. It doesn't have to be I, it could be actually any letter. I is the most common, sometimes we see K, sometimes it's actually N there, and then there's actually a number on top. So that's the notation. And it's basically, it's telling you, you need to add these up. It's an action you do. Much like, we actually use this a lot when we do an average. So, oops, I thought I was on my pen. So in statistics, you show an average of something as having x bar. And we write this as the sum of all the x over n. So that's kind of our saying that you're adding up all of your values and then you divide by how many there are. So that's how we use summation notation when you're in statistics. So here's an example. Find the sum and verify with a graph. So I've got our summation notation here. And so we're gonna just kind of write it out. So each term I'm plugging in the new value for I. So I have I equals 1, I equals 2, I equals 3, and so on. So 2, I have 2 times when I is equal to 1, so that's 2 times 1 minus 1. I'm going to just put brackets around there, so that's the first term. Now we're counting the i's, so now I is 2. So that's 2 times 2 minus 1. And then I move to I equals 3, so that's 2 times 3 minus 1. Then I equals 4, so that's 2 times 4 minus 1. And then we stop at 5 because that's the number on top, 2 times 5 minus 1. So I have 5 terms here that I've added up, and now I'm going to have to actually simplify these. So this is 2 minus 1 plus 4 minus 1 plus 6 minus 1 plus 8 minus 1 plus 10 minus 1, which is 1 plus 3 plus 5 plus 7 plus 9. And when you add all those up, you get 25. So that is our sum for this sequence of values. And when you have 1 plus 3 plus 5 plus 7 plus 9, that is called a series. That is a finite series. So I have this graph here. Desmos has a way to do summations, and so I found a template, and then I basically modified it. So I'm going to click on that and open it up. And then here we go. Okay. So it has these little tabs things that you can open up. So here is just basic. So if I want to just find the sum, we're starting at 1. You don't have to use n, you can say I. So I could change this to I. And then change this to 2i minus 1. And then this goes to 5. Now notice this says 29. Because, and it took me a while to figure this out, when it's only doing the sum of 2i, and then at the very end it's minus 1. So if you want this whole thing, you have to put parentheses around it. So parentheses are really important to indicate, because otherwise it's assuming you're only doing the 2i. So that gives us 25. That's the same answer we got by hand. Intermediate here is how we graph this. So they use k, so you could just change this to I, but there's a lot of things to change here. So we have, this would be 2i minus 1 or 2k minus 1. So I modified this from what it was. And then we're counting some ending point, and so I set that as 5. We're stopping at 5. And then here, again, see, if you don't put in those parentheses, it's really important. So you have to have those parentheses, and then it's doing the sum, and it's, again, telling you the sum, and then it's actually graphing it. So when you look at the graph here, these red lines are sequence values. So you want to look at the y value. We got 1, 3, 5, 7, 9. So those are the first 5 terms. And then this is the sum as the dashed line. So that's telling you where the sum is, and that is 25. And if you wanted to, you could do more terms. You can see the pattern, but the sum is going to keep increasing, and it increases off of your screen if you do that. We also have advanced here. Don't worry about advanced. You're not going to have to do anything like this. There's an alternating sequence template. We will talk about those. These Taylor binomial series, Riemann sums, these all come up in calculus. So if you want to save this later for when you're in calculus, that's what this advanced tab would be. Otherwise, all we really need, you just need the basic or the intermediate. So I'm going to save this with all of my changes there. All right, so moving on, example 9 here. So use sigma notation to write the sum. And now this one is written in a way that's easy for us to determine what's changing, because you can see we have 1 plus 1, 1 plus 2, 1 plus 3, and so on in the denominator, so it's a lot easier to determine what the pattern is, because they've written it out for us. So if we start with n equals 1, n equals 2, or I should say I, because we're using sequences. And this is I equals 3. that means we must end at I equals 15. So I'm going to make my sigma. The bottom number is where you're starting with, so that's I equals 1. The top is where you're ending, which is at 15. Then you write your pattern, 5 over 1 plus, and then the number that's changing is I. So that would be writing that in sigma notation. So that one's nice and easy because it's basically they've formatted it for us. Here in example 10, this one is trickier because it's not in a particular format for us. So I'm going to actually kind of write just the sequence part of it. So that, oops. And then write my ends. So this is n equals 1. Actually, I should say I. I equals 1, 2, 3, 4. And then we don't know because we just stopped at some point. So we're trying to find a pattern here. So I notice that they're alternating in sign. So our general rule when we're all, I should start my notation. I equals 1. We don't know where we're stopping, but generally when we are alternating, it's -1 to some power because that's the easiest way to alternate in sign. So looking at these, and I'm going to just look at the denominators here. This is 2 to the first power, 2 to the second power, 2 to the third power, and then this is 2 to the 7th power for 128. So you notice that there is a pattern to the denominators. And basically the power is 1 less from what your I is. And if we do 2 to the 0, and it's 1 less than the I, that would work. So we have what's looking like 1 over 2 to the I minus 1. So now let's just kind of test this out. So if I is equal to 1, I get -1 to the first power over 1 minus 2 to the 1 minus 1. And this actually gives me -1 times 1 over 2 to the 0. So that gives me a -1, but I want a +1. So my signs are currently in the wrong direction. I can fix that by just doing an I minus 1 up there. Because then this would be 0, just like it would be 0. -1 to the 0 is 1, and then that would work out. So always double check what you have, make sure all your signs are right. Now the way we've written this, we have to figure out, okay, where do we end? So 2 to the 7th was the last denominator, and if those exponents were 1 less than I, so that means I must be 8. So I finished my 8 there. And now let's try to neaten this up. So I'm going to have my sigma notation, I equals 1 to 8. And notice that they have the same exponents, the -1 and the 2. So I could write this as -1 over 2, and then I minus 1 like that, where it's just -1/2 to the I minus 1 power. When you try to, the negative is still getting to the I minus 1, and when you distribute that exponent, it's going to come out exactly the same. So that's a different way to write it, a little easier way to write it. So that would be our sigma notation. Now, if you are someone that doesn't like having I minus 1 up there, you can also write this in terms of I equals 0. But if we count from 0, then we must only go to 7 because we're just shifting over where we're starting. And then if we start from 0, we don't need to subtract 1 anymore. Oops. We can just put I up there in the denominator. So if you shift your index down, then what happens to the actual, let's highlight this. If this index goes down by 1, the top has to go down by 1. But what happens then is that the actual term that creates the sequence or the series, that goes up by 1. It kind of does the opposite, it goes up 1. that relationship is something that you will need when you go to calculus, when you start talking about these sequences and series in calculus. You don't need it so much this class, but just keep that in the back of your mind going forward. Now these are some properties of sums. Basically, that if you have a constant, you can pull the constant out from a sum. If you have two things added, you can split them up as two different sums. Same thing with subtracting. You don't really need these until calculus, but they are presented in the textbook. Now I've mentioned the word series here. If you're adding terms to a finite or infinite point, that's what you have. You have what is called a series. And so when we're finding the sum of a sequence, that is actually a series. If it has an ending point, we call it a finite series. Otherwise, it's an infinite series. And when we're finding the sum and we're not going forever, we could say it's a partial sum because you're not adding everything, you're only partially adding up. So this is my last example for this presentation. Find the third partial sum and the sum of the infinite series. So this is an infinite series because our ending point is infinity, it's not a number. And in this case, instead of I, we're using k, but that's completely fine. So third partial sum, that means that we are doing a1 plus a2 plus a3. So we're doing the first three terms, adding those up. So we're going from k equals 1 to k equals 3. So the sum from k equals 1 to 3 of 1 over 10 to the kth power is 1 over 10 to the first plus 1 over 10 to the second plus 1 over 10 to the third. So that is equal to 1/10 plus 1/100th plus 1/1000th, which I would just use my calculator to add those up. We got 111 over 1000. So that is the third partial sum. Now, how do we find the sum of an infinite series? We're not going to literally add everything up and go on forever. Like that doesn't make sense. You don't want to do that. What we do is we look for the pattern. So we're just saying, let's say the first partial sum. That would be only that first term, that's 1 over 10, which is equal to 0.1. The second partial sum would be adding the first two terms. 1 over 10 plus 1 over 100. So when you do that, and I'm going to just make this a decimal so you can see the pattern a little better, that's 0.11. We already know the third partial sum. When I make that a decimal, it's 0.111. So you can see there's a pattern. With each term we add another 1. So if we go on to infinity, we're going to get 0.11111 and so on. That just goes on forever, which is the same as just 0.1 with a line on top to indicate the 1 repeats forever. Well, 0.1 repeating forever, that is actually a fraction. That is actually a rational number. That is equal to 1/9. So that means our sum of the infinite series is 1/9. And we figured that out by finding the pattern and then determining what number we are approaching. So that's how you find the sum of an infinite series. You look for a pattern and then you see, oh, I think I know what number this is. What is this number? So that is it. Hopefully all of the sound on this one and I don't have to is there. I don't have to record it another time. Crossing my fingers, I'm definitely gonna have to play this again to verify, and then obviously you'll know when you get this. So if you have questions, you guys can email me, give me a call, message me through Remind, and I hope you guys have a great weekend. Bye.